Welcome back to Concepts in Arithmetic. Let me just scoot up here. In this video, we are going to discuss exponents. So there are a handful of rules for exponents that I'm sure you remember from your high school algebra. And you'll remember that our author has a couple of classifications. We have the properties, identities, and rules. Okay, so the properties of the number system are things like the associative property of addition and multiplication, the commutative property, the distributive property. Those are properties. An identity is any equation that is true no matter what values the letters represent. And a rule is an identity that comes up so often it's worth memorizing. So these rules for exponents fit into that category. So you might remember this: if you have two powers multiplied, you can add the exponents. And this just comes from counting factors, okay? Let's do a concrete example. 2 power 3 times 2 power 7. Well, the notation of exponents tells us how many factors we're going to have. So this part of the expression is going to have 3 factors of 2. And this part of the expression is going to have 7 factors. And we're multiplying them. Okay, so by the kind of associative property, we can kind of basically ignore the parentheses right here. So we have 10 total factors. So 2 power 3 times 2 power 7 is 2 power 10. Okay, now this is actually useful for helping us with some mental math. If we were presented with the problem this way, it's much easier to, rather than trying to do 8 times 128, do 2 power 3 times 2 power 7, which is what both of these are. Use the rule for exponents, that's 2 power 10, and since we know our powers of 2's, we know 2 power 10 is 1024. Okay? Oh, and here's an interesting little applied problem. So a germ cell divides every hour. We want to estimate how many of these germ cells there will be in 36 hours. Okay, well, we start out with 1, and then after an hour we have 2 because it's divided. Now there are 2 copies. And then after another hour we'll get 4 because we have 2, and then each of those divide, giving us double what we had an hour before. And then after 3 hours we'll have double that for 8, and so on. We're letting this happen for 36 hours, so we're going to have 2 to the 36. Now, I don't know what 2 to the 36 is. I remember my powers of 2 up to like 2 to the 10, which is 1024. Right? I know 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. I guess 2 to the 11 is 248. You kind of get that one for free. But I have no idea what 2 to the 36 is. And it would be difficult to do that mentally for sure. Okay, so here's how I'm going to work. Okay, 2 to the 36, if I use my rules for exponents backwards, it's this right here. Doing some weird stuff there. Let me see if that fixes the problem. Okay, if I use my rules for exponents backwards, I get this. I can replace my 2 to the 36 with 2 to the 10 times 2 to the 10 times 2 to the 10 times 2 to the 6, right? 10 plus 10 plus 10 plus 6 is 36. Now I know each of these. Each of these 2 to the 10s is 1024, and the 2 power 6 is 64. Okay, well, if I'm estimating, I don't calculate with 1024, calculate with 1,000. Okay? So in other words, get rid of my punchline there. This is approximately equal to 1,000 times 1,000 times 1,000 times 64. Or if we want to do an even better estimate, let's just call that 70. Round these down, round this up. That would be 70 billion copies of the germ cell. Okay, so in 36 hours, if that one germ cell is dividing every hour, in 36 hours you got 70 billion germ cells. Approximately. Okay. You probably remember this rule for exponents as well. You've got division, that translates into subtraction in the exponents. And of course that comes from the factors canceling between the numerator and denominator. Okay? So if I had 2 power 5 divided by 2 power 3, that literally means this. Notice in the top I've got 5 factors of 2, down here I've got 3. So I can cancel 3 factors, top and bottom. That leaves me with 2 factors of 2 left. Okay, and by a similar method to what we just used, we can sneak in these powers to help us do some mental math, especially since we know our powers of 2. Okay. One thing I would note is that the rules for exponents apply when you are multiplying and dividing. The rules for exponents don't work with addition and subtraction. So in other words, this can't be simplified. The rules for exponents count factors. So this has 2 factors and this other part has 3 factors and they're both multiplied. These guys are not factors, they're terms. So the rules for exponents don't work there. We've got rule 3 and 4 here. Rule 3 says if you raise a power to a power, you can multiply the exponents. And that actually comes from, really from rule 1. That we discussed earlier in this video. Okay, if we take this specific example, 2 power 3, and then we're going to take that and raise it to the 4th, well, in mathematics, we have to follow the instructions literally. It says we are going to do 4 copies, 4 factors of this right here. So we have 2 power 3, 2 power 3, 2 power 3, 2 power 3. And my first rule tells me what to do when I'm multiplying powers of the same base. I can add the exponents. So my exponent would be 3 plus 3 is 6, plus 3 is 9, plus 3 is 12. This would be 2 to the 12. In other words, the new exponent would be the product of these 2 exponents. And this rule here tells us how exponents work with products of 2 different numbers. Okay, so if I'm taking a product to a power, I can take each factor raised to that power and then do the product. And this comes from the commutative property and the associative property working together. Let's look at a specific example right here. If I had 2 power 4, and once again I'm in the way, let me scoot over here, maybe. Okay, let's say I had 2 power 4 times 5 power 4. Okay, well, I could try to figure these out individually and then multiply them. Or I could use the rule that we just discussed. It says that this is equivalent to this right here. Now these intermediate steps are kind of me demonstrating why it works. Okay, 2 power 4 means 4 factors of 2. 5 power 4 means 4 factors of 5. Now, multiplication, I can do these in any order. So I don't have to do 2 times 2, I could do 2 times 5. And then I could do another 2 times 5. I could pair up every 2 with every 5. In other words, I could do 2 times 5 power 4. Now this is much easier because 2 times 5 is 10. And I know how to do powers of 10 very quickly. 10 power 4, that's 10,000. Okay, so these rules for exponents are meant to give us some flexibility. It doesn't say if you see this, you have to turn it into this. No, it says if you're working with this, and it would be easier to work with this, then you can make that switch. Okay? If it's better off the way it is, then leave it as it is. However, if this makes it easier, you can change it. Okay? It gives us that flexibility. Let me do an example down here. I want to simplify an expression here. So I'm going to use the rules for exponents to help me simplify this expression. And the expression I want to work with is 2 power 5 times 6 power 2 times 18 power 2, whole thing over 3 power 4 times 4 power 2. Okay, now, if I were to try to power through this and do the multiplication and then do the division, I'd be working with some large numbers because things get big pretty fast when you deal with exponents. So I want to avoid that. What I'm going to do here, I notice that, well, everything is even, so that's, well, except for this. This has factors of 3. Okay, these are all even. Even means I've got factors of 2. Everything here has factors of 2. And these guys have factors of 3. Okay, so I'm going to try to write everything using the factors of 2 and 3, then apply the rules for exponents. Okay, I'm going to write everything using factors of 2 and 3, then apply the rules for exponents. How about I go over here? All right, so 2 power 5, well, that's just 2 power 5. Now 6, okay, we know 6 is 2 times 3. So instead of 6 power 2, it's 2 times 3 power 2. 18 is 2 times 3 times 3. Okay? Okay, 3 to the 4th, can't do anything with that. 4, I know that, that's 2 times 2. So instead of 4 power 2, it's 2 times 2 power 2. Okay, now I'm going to apply rule 4, the one that we just went over, okay, that deals with products raised to powers. I'm going to apply that to the numerator and the denominator. Okay, so this right here, instead of 2 times 3 power 2, it's 2 power 2 times 3 power 2. And this is 2 power 2, 3 power 2, 3 power 2. Okay, so I apply rule 4 and I get that. Now I'm going to collect all the 2's and 3's, because remember, exponents are just counting the factors, right? So what I've got here in the top, 2 power 5, that's 5 factors, 2 more, and then 2 more. So in my numerator, I think I've got a total of 9 factors of 2. Let's see how many factors of 3 I got. Looks like I got 6, 2, 2, and 2. So 2 power 9, 3 power 6. Down below, what do I have? I have 3 power 4 and 2 power 4. Okay, so to get from here to here, we were applying rule 4. Okay, now I've got some division here. Oh, sorry, I guess this is rule 1 here to deal with adding up the exponents, that first rule that we talked about at the start of the video. Now here, I've got division, okay? And the rule for exponents involving division, that was rule number 2. It says I can subtract the exponents. Up top, I have 2 power 9. Down here, I have 2 power 4. So this is 2 power 5. 3 power 6 over 3 power 4, that's 3 power 2. So this is 32 times 9. Oh, easy mental math, right? We know a trick for multiplying by 9. Hit this with a 10, 320. Subtract 32. 320 minus 30 is 190, and then 320 minus 30 is 290, and then minus the additional 2 gives me 288. Okay, so this very complicated thing that if we tried to slog through it directly, we'd end up with dealing with very large numbers. The rules for exponents allow us to do this just with some counting, okay, because that's what exponents do. They count the number of factors. Okay, so a very nice way to simplify an expression like this. The key is break things up into the factors and then use powers of those component factors.